Solve. All right, for example A, we have an equation that has 3 logarithms. Remember that we cannot solve equations that have more than one log on each side of the equation, so we're going to have to then condense this by combining 2 of the logs at least. All right, so this actually isn't too bad. We're just going to rewrite this as a single log. Remember that a sum here can be expressed as a product. And the way we're going to do that is we're going to write just one log, right? Base 7, and then multiply 3x and 2x minus 1. And that will be equal to the log of 16x minus 10 base 7. Now here we have a situation where we're taking the log of both sides of the equation, and the log we're taking has the same base in both cases. So that means essentially the only way the two sides could be equal to one another is if this piece is equal to this piece. So in other words, we're going to be able to say that we can drop the logs here on both sides of the equation and just say that we have 3x times 2x minus 1 is equal to 16x minus 10. So that makes it nice and easy. From there, distribute in the 3x here. So we'll have 3x times 2x is 6x squared, and then 3x times a negative 1 is a negative 3x, and that will be equal to 16x minus 10. From here, we have a quadratic, so bring everything to one side and try to solve. So we'll have 6x squared minus 3x. If I bring over the 16x, it'll be negative 16x, and if I bring over the negative 10, it'll be positive 10, and all of that will be equal to 0. Then combine like terms. So negative 16x and negative 3x make a total of negative 19x plus 10 is equal to 0. And then we're going to try to factor this if we can. So we'll try, for example, 3x and 2x. Then we might try 5 and 2. The reason why I didn't put the 2 in here for the 2 and 5 is because I don't want to have like terms if the original polynomial did not have like terms, right? Remember that. It's an important principle. Then from there, because of the plus sign on the 10, I know it's going to be 2 negatives, right? Because the sign here is negative. And then we can check the middle term. This will give us negative 4x and then negative 15x. That does indeed add to negative 19x, so the factoring is correct. And that means that we can separate these two binomials and set them equal to 0. And we'll end up with 3x is equal to 2, or in other words, that x is equal to 2/3. And then we'll end up with 2x is equal to 5, or in other words, that x is equal to 5/2. All right, so finally, the last step of this is actually to check. We always have to check our answers because it's very possible that we can have an error in the domain, right? So we want to make sure that both of these are acceptable solutions for the equation. Okay, you can check these answers by just plugging them in for x. You can use your calculator to do that, or you can do it by hand. Either way, they actually both do check out, so I'll leave it up to you to check those. For now, let's look at example B. For example B, it's very similar. We have 2 logs on the left that have to be rewritten as a single log. Here they both have base 3, so it's possible to rewrite them as a single log. And since it's the sum of 2 logs, we can express it as the log of the product of the 2 things you were taking the log of, right? So let's go ahead and do that. We're going to write down just the single log base 3, and then we'll have x plus 1 times 2x. And that'll be equal to log base 3 of 3x plus 1. And this is actually nice because remember, whenever both sides of the equation have the same log being taken of the entire side of the equation, that means that the only way the two sides of the equation are equal to one another is if this piece is equal to this piece, right? So let's go ahead and do that by dropping the logs and saying that it must be true that x plus 1 times 2x is equal to 3x plus 1. All right, then we could distribute in this 2x. So x times 2x is 2x squared, and 2x times 1 is plus 2x, and that'll be equal to 3x plus 1. Then we bring everything over to the other side here, so we're going to bring the 3x and the 1 over, and the reason why we're doing that is because it looks like this is a quadratic equation, so we must bring everything to one side and set it equal to 0. So this cancels out. We have 0 on the right-hand side, and we end up with 2x squared minus x minus 1 is equal to 0. Let's try to factor this. So we'd have 2x and x. All right, so factors of 1 in this case will be 1 and 1. Of course, we don't have any choice there. And because of the negative, it has to be a sign of each, right? So we can try plus and minus like that. So let's see what happens here. We get 1x, right? And then we have 2x times negative 1 is negative 2x. So that gives you a total sum of negative 1x. The middle term is therefore correct. So we can go ahead and say the factoring is good here. So let's go ahead then and separate the factors separately equal to 0. So 2x plus 1 is equal to 0. X minus 1 is equal to 0. That means that x is equal to 1, or that 2x is equal to negative 1, or in other words, x is equal to negative 1/2, right? So two possible solutions here. I think we're going to have a problem with this x equals to negative 1/2. What would happen if I put that in right here? Well, then we'd end up having what? It would end up giving us the log of 2 times negative 1/2. The 2's would cancel out, giving you log of negative 1, which isn't defined. So we're going to say that this is not a possible solution. Let's go ahead and check the x equals 1 just to make sure that works. If we plug 1 in there, we're going to end up having log of 1 plus 1, or 2 base 3, plus log of 2 times 1, which would be 2 base 3, right? And then that'll be equal to log of 3 times 1, or 3 plus 1, which is 4 base 3. And this is in fact correct, because remember that a sum of two logs can be written as the log of what? The product, right? So 2 times 2 is 4. So we have that log of 4 base 3 is equal to log of 4 base 3. That makes the solution valid. So x equals to 1 is our only solution for example B.